And we will move on to another remote participation now by Nancy Klimas from Institute of Neuro-lmmune Medicine in the Nova Southeastern University, not the Nova Medical School. And this is because we have an university in Lisbon with the same name. And we will talk about comparative analysis of pre-pandemic ME/CFS and long COVID cohorts, phenotyping insights, and Sipavibart monoclonal antibody trial. Thank you.
Hi, thank you for having me. And can you see my slides okay? Everything's all right? So I'm assuming you can hear me and you can see my slides. Is that all right? All right, well, I think I can see it on the screen, maybe. Okay, anyway, hi, I'm Nancy Klimas from Nova Southeastern University in Fort Lauderdale, Florida. And I've been doing a lot of ME/CFS research for many, many years, and more recently, long COVID. And thank you for having me. I'm actually in Australia right now. They're having a competing meeting, and I'm somewhere near Brisbane. So my world is upside down time-wise. Can you see that? I can't tell if you can see my slides. Yes, they're right. Now I see it changed. Great. Okay, so I'm assuming you can hear me and you can see, or you would interrupt me. So today I'm going to talk about a couple of things. They sort of morph together. But I will be talking about ME/CFS and long COVID, some of the things they share and some of the places where they are not sharing exactly the same thing. It starts with a trial that we're doing. This study, it's not a trial, I'm sorry, it's a study, COVID-19, Understanding the Post-Viral Phase, or COVID UP. This is a CDC-funded study with a cast of thousands, a lot of people working in this study. We've been at it for a number of years now. We're just in the final month or two, so we're excited that we reached our recruitment goal of 800 people with 600 long COVID and 200 recovered, of which we brought in 200 people, 150 ill and the 50 recovered for phenotyping studies. So that's one study that we have underway. And the main thing here, as you know, is that there's so much similarity between ME/CFS and COVID that we wanted to explore, that area, because we're taking advantage of this other study that we completed right before the pandemic, MCAM, which is another CDC study that had 750 patients, another very large cohort. This was from, I think, 7 expert clinics. Where we really diverge in terms of who we're studying is the COVID UP study is regional, it's South Florida, and it's representative of the population, meaning that we recruited from healthcare systems, not clinics, including the healthcare systems that serve the underserved. So we have a socioeconomic distribution, racial distribution, ethnic distribution that's much more reflective of the place we live. And so we're very excited about this study. Unfortunately, I'm going to say that because the CDC has been in government shutdown for the last 6 or 7 weeks, I couldn't get permission to show the most recent data. So I'm going to do this just a very brief thing here and hope that you invite me back next year when I can have all the final data in hand. But that lets me concentrate on my other things as well. The second study that I will be talking about is this study. This is a monoclonal antibody study, a therapeutic intervention, double-blind placebo control of a monoclonal against spike protein. This is the AstraZeneca product that is used to prevent COVID. And it has gone through some iterations. This is their more recent variation that covers variants through about the middle of the Omicron change. So Omicron, like early 2024 backwards to the beginning. So we're excited about this study because we did a little open label case series, or I should say Dr. Shepke did, one of the co-investigators, with a case series with a different product. And he had some remarkable improvements in some of the patients who received the monoclonal, which led on to developing this study. So what do we need to know about what's the same and what's different, and what we can learn from both what we hope to be able to generalize from one to the next as we do these really important evidence-based studies, so that we can say that with certainty what is the same and when can generalize. Well, they share clinical phenotypes, as I showed you in that first slide, they're widely overlapping both in the way they present and the severity of the presentation, which I'm sure you've heard from others, and I won't belabor the point. The triggers are different, and this is important because I threw in a third illness here. Long COVID, clearly the trigger was SARS-2 infection. ME/CFS, more often than not post-viral, not always post-viral, but more often than not post-viral, but not necessarily a specific virus, Epstein-Barr, influenza, other types of upper respiratory tract infections, enteroviruses, and so on. Now, Gulf War illness I threw in because Gulf War illness is a toxic injury. These are the veterans that were sent to the Gulf 1990, 1991, and they had tremendous organophosphate exposures and other burn pit exposures, burning gas wells or oil well exposures. They had a tremendous toxic load. And their end result was a chronic neuroinflammatory state. So if you look at all these different illnesses as being triggered by different triggers, but having sort of a common persistent illness with common persistent mediators, they can be lumped, and we can learn from what we learn from one and hope to apply it to another. So the working model then here is that there are triggers, and these triggers can be viral or not, specific viruses or not. Chronic immune activation persists or goes on. That results in immune senescence and poor immune function. Viruses reactivate. Viruses reactivate continuously, push the on button and keep that immune activation going. And eventually there's immune senescence and more viral reactivation, a vicious cycle. Spin-off from that, from the speaker we just heard before, is Carmen's work, very important work on the autoimmune mediators, because autoimmunity is also a chronic immune activation, thumb on the go button kind of push that results in senescence and so on. And you could postulate that the autoimmunity happens early in the course of the illness, but you could also postulate that any illness that results from chronic immune activation initially could eventually start spinning off autoimmune mechanisms, particularly when Epstein-Barr virus is involved, since it's a polyclonal activator that's known to trigger autoimmunity. So all of these things that drive the immune system into a chronic immune activation state is a setup for viruses to reactivate. And then the viruses are also contributing to the mediators of the illness. This is one of those lovely summary slides that tries to make the point about what is the same across the board. And you can see that all three illnesses, because I included Gulf War illness on this, have evidence, whether it's looking through the cytokine window or the immune window or the proteome window of chronic immune activation. And in fact, this is one of the very first things noted in ME/CFS in our first paper, which was in 1989. It was actually the title of the paper, Chronic Immune Activation. And same with Jay Levy, who published the same year in The Lancet. So that one of the very earliest immune findings in ME/CFS was chronic immune activation. And both those papers also emphasized the poor cytotoxic function and evidence of EBV reactivation in patients with ME/CFS. Since then, as we've gotten new markers and better ways of measuring, the senescence markers were measured, and there they were. The immune senescence was a part of the play here. And another cell that responds very poorly to chronic immune activation is the mast cell. And you will see patients often have an overlay of mast cell activation syndrome at a low level or a high level. And it becomes another cell that releases all kinds of chronic inflammatory mediators. and helps drive the severity of the illness. Finally, I put the gut microbiome on here, not technically part of the immune system, but another thing that can drive immune dysfunction, particularly when there is mucosal integrity breakdown and antigen exposure systemically to a broad spectrum of antigens that would normally be hidden from the systemic immune system through barriers, through mucosal barriers. So that's sort of a breakdown about if I were to split it into innate versus adaptive immune system. The innate immune system is really important here, and that is this very clear evidence that natural killer cells aren't working correctly. In fact, when the Institute of Medicine did an entire review of the literature about 8 years ago, they said it was the one single marker of immune dysfunction that they would accept as evidence-based. Everything else they thought at that point, I think it's much better now, but that point, the lack of validating studies, so many intriguing papers without the follow-up high and number drove some of their conclusions that everything else was more intriguing than definitive. But NK cell they thought was definitive then and listed it as a biomarker of NK, of ME/CFS. So you can see NK cell dysfunction is a player, and many groups have published this now. We published it, like I say, in the early 90s, but many times since with different cohorts. But so have other groups. And in fact, Dr. Marshall Gradisnik, who's actually hosting the conference I'm attending right now in Australia, their group has done a lot of work looking at the TRP channel dysfunction in ME/CFS, and they have a very elegant system now to test ways to correct that, and presented at this conference an intriguing paper that low-dose naltrexone actually helps correct the channelopathy that you see, this calcium influx channel dysfunction of NK. It helps to restore NK cell function. I think that's fascinating because clinically we use a lot of low-dose naltrexone thinking we're working on neuroinflammation, but in fact it has a much broader effect. And then our group has published papers using flow cytometry to measure the content of the NK cell for granzymes and perforins as being reduced in all three conditions: Gulf War illness, ME/CFS, and long COVID. In terms of adaptive immune changes, you just heard an elegant talk. I hardly need to spend time on this slide because you just heard it all by the foremost authority, I think one of the leading experts in what's going on with autoimmunity in these conditions. And Carmen just did a splendid job of describing the T cell and B cell compartments. So I'm going to bring you down to the bottom of this slide, the key question. If chronic antigenic stimulation is driven by antigen, it can be autoantigen, or it can be non-self, it can be self, autoantigen, or non-self, pathogen. So key question in this illness is what is driving the illness, or at least the chronic immune activation component of the illness? Is it reactivated infections, or is it autoantigens, or is it both? And I can tell you, since we measure this all the time, we frequently see both, frequently. But we nearly always see reactivated infections. So a part of the problem, as you know, is that with autoantigens, you have to know what you're looking for. You have to order the right test. And the work that Carmen's group has done looking at the alpha adrenergic and beta adrenergic receptor autoantibodies in these illnesses is really pivotal. But there are other autoantibodies, including CNS autoantibodies, that have been reported. And it's hard to do a total body survey. So I think at the end of the day, when you're a clinician, you have the data you can collect, and it can be, well, look, there's evidence of EBV, perhaps CMV, perhaps HHV6 reactivation, and maybe I have a low positive ANA, and now I'm going to go searching for autoantibodies as well, just to try to hone in what can I try to fix, how can I help this patient? But since this talk is going to speak mostly on viral reactivation, I'll focus on that. And this is some of the information we know about that. Well, Much of the focus has been on herpes viruses because they are latent, they reactivate, they cause all kinds of havoc. And there are some treatments available. And so there's more than 1,500 pages in the ME/CFS literature on viral reactivation, or that shows evidence of viral reactivation in the literature. And it's more likely to happen and at higher levels when NK cells are dysfunctional, that's been shown, or cytotoxic T cell function is impaired, or both. So the degree of immune dysfunction drives or predicts the level of viral reactivation that you will see. In long COVID, though, we have another whole thing, and I'm going to spend a little time on this because it's the reason why we're doing that monoclonal antibody study. In long COVID, there appears to be a reservoir of viral antigen in people with long COVID that persists months and years after the primary infection. So you could argue that there's viral persistence. I don't think we have evidence to prove that. It could be a hypothesis, but we have absolute evidence that there's spike protein and nuclear antibodies, but particularly spike protein reservoirs hiding in organs and bone, and to some extent a little bit in plasma. So that's a hell of an antigenic drive, and it can be a really important reason why people keep their immune system so stirred up and so dysfunctional. But also in long COVID, if a person reactivates EBV during primary infection when there's acute COVID, that's a predictor for long COVID. So people who reactivate EBV, which is about 40% of people, that's a predictor of people who go on to be at risk for and eventually develop long COVID. Also, people with long COVID who have reactivated virus, the more virus they have, the sicker they are. It does predict the severity of illness. So again, we're stuck in this loop that I was describing: viral reactivation, inflammation, senescence, cellular exhaustion, poor cell function, more virus comes out, and on it goes, round and round in a big circle. So as I said, there's more than 1,500 papers in ME/CFS because we've been doing this since the 90s, so there's been some time to do some papers. The focus has always been on herpes family viruses, primarily EBV and HHV6 being the most commonly seen, HHV6 being the most commonly seen. CMV also seen, though sometimes not in the blood compartment. Enteroviruses, particularly Coxsackie B virus, in the gut compartment, not circulating in the blood. So you actually need to look at the person who did all this work was John Chia, and he looked at people who went in for endoscopy for any reason. And he did 300 plus endoscopy reviews for viral reactivation in people with and without ME/CFS, and had a very high prevalence of Coxsackie B, but also EBV and CMV in those stained tissues. And he did some very elegant fulfilled Cox postulates type of work to prove that the enterovirus was in that compartment. We sometimes see parvovirus, and that's actually treatable. So when you see it, it's kind of nice to find it because you can do something. And that is an important player. I think I sort of reviewed this, that EBV, we mainly are monitoring by antibody response to antigens that shouldn't be circulating, specifically early antigen, that's probably your best. But also we often see IgM antibody to capsid, which is, the outer wall. And IgM antibody is not something you're supposed to see after primary infection. So two of the big serologic indicators of EBV reactivation are high titers to early antigen and high titers to IgM titers. When the Stanford group did a Val site study, and they looked at who the responders were and who weren't responders, they said EBV early antigen titer of 1 to 160 or greater predicted a responder, and 1 to 80 and lower were less likely by a lot, like a 5% response rate versus a 60 or 70% response rate. So that was quite the line, or IgM positivity. So I thought that was a pretty good clue, and we thank Dr. Montoya for giving us that important information. Finding the PCR positive is trickier because it comes and goes. And the time when they found PCR positive in the plasma of MD patients is when they've done longitudinal studies and drawn it 3 or 4 times. And then particularly with HHV6, Dr. Connie Knox did a study with HHV6 with 4 blood draws, and she found it in a very high level. It was more than 80% by PCR at least once. So that was important. And the other thing that's not published, but Dan Peterson did this study, is he did spinal fluid, and he did around 130 spinal fluids of the sicker end of ME/CFS, and found 44 patients out of 130 or so PCR positive for HHV6, and then in the teens for EBV and in the single digits for CMV. So he was actually finding viral DNA in the spinal fluid in a significant portion of ME patients, and I think that's rather important. Another important study is Dr. Marshall's group at Ohio State. This is really important work because it kind of turns on your head what you thought about viruses. Do I need a whole replicative virus to mess someone up? And they're saying, no, you don't. If there's a latent virus like EBV or HHV6, and there's a lot of immune activation, there's enough viral code in those cells to be coding for viral peptides like DUPTase. And DUPTase itself has a lot of immunologic and endocrine effects. And so they're saying you don't need a whole replicative virus. You don't need Cox postulates here. You need viral enzymes that are unique to these viruses being expressed by the cells that are infected by these viruses. And they've done elegant work, very definitive work, that DUPTase is a player and part of the problem in these illnesses. So this, on the yellow on the bottom corner there, is this DUPTase slide from a paper that they wrote not too long ago that's looking at reactivation of EBV and HHV6 and all the effects the DUPTase enzyme can have on, in this case, just the immune cells. There's also a whole host of endocrine things DUPTase affects over and above the immune system itself. On the left, I'm showing you a picture from a different paper from Verma et al. That shows the role of co-infection. What happens when you have more than one virus? And during your acute COVID, if you have, the first slide there shows a virion binding to the ACE receptor with just COVID on board. And it says 3 spike proteins bind to the ACE2 in that setting. The middle slide adds Epstein-Barr virus to the culture. Now 4 spike proteins bind to ACE2. You have a different level of binding and a different level of drawing that virus into activating cellular processes. Finally, that third one is when you're co-infected with EBV and HHV6, 2 co-infections plus COVID, and now you have 5 spike proteins binding to ACE2. So you can see that viruses, when they come together, help each other be even more equal. And that's what that slide is suggesting. So we have to think about co-infections and that we're not necessarily looking for the magic button, the single virus that's causing all of this problem. So here's some of the data that EBV reactivation predicts long COVID and has an impact. And here's now 1, 2, 3, 4, bunch of papers here, what, 5, 6 papers that look at Epstein-Barr virus in long COVID. And it's showing that it's reactivated, that it increases the severity of symptoms, that it's associated with very specific symptoms like brain fog, headaches, confusion, that 42% of long COVID patients are demonstrating EBV reactivation in this 2022 series. I've seen other series much higher, the one here 66%, and so on. So it's a player. What about HHV6? We talk lots about EBV, and we should. It's a bad bug. but HHV6 is there too. And as I said, I showed you the DUPTase data, but it's a frequent co-infection, and it's activated in long COVID in a significant subgroup. It's also associated with autoimmunity and oxidative stress and inflammation. And when you have EBV and HHV6 together, you're sicker. Enteroviruses, I mentioned Dr. Chia's work. I'm not going to spend a lot of time on it, but I wanted to make sure I didn't just talk about herpes family viruses. And we've been having discussions about retroviral fragments for a long time. You know, we have a lot of endogenous retrovirus in our DNA, and whether or not we should be completely ignoring that, you know, you could argue that, particularly with the work in ALS and other diseases, they're starting to make endogenous retroviruses more important in brain diseases, that we should be paying attention. The other thing about co-infection is we learned a lot in HIV about co-infection, because co-infections made HIV much worse. If someone had acute EBV or acute CMV, at the time they got their acute HIV, they were dead in 5 years. It didn't take them any time to totally shred their immune system. So that was because during acute infection, when you have one of these other herpes viruses and you have a virus that is being produced, it actually upregulates the amount of virus, and then you end up with a much higher latent viral load and a much more potential to have chronic immune activation driving persistent infection as it goes along. So as we puzzle our way through this long COVID question of why are we seeing spike protein 2 years, 3 years after the acute infection, it begs the question, is it a deposit of old spike protein? It all happened during acute infection? Or is this the weird, strange SARS-2 infection that should not be, that persists? Because SARS-2 is like 30% of your common cold viruses or coronaviruses, right? So they should come and go. They shouldn't hang out. But, you know, mutations happen and viruses change, and perhaps we don't really know what's going on that's driving all this spike protein to persist for years after an acute infection. But what we do know from HIV is that if you had co-infections, that wasn't good for you. And it created senescence, T-cell exhaustion, early aging, short telomeres, and so on. So how's that relevant to long COVID, ME, and to our Gulf War veterans? These common mechanisms across all these different illnesses, knowing that they correlate with severity, they correlate with the way the illness presents. It makes total sense that if your cytotoxicity is not working, you're going to reactivate viruses. And whether or not this persistent antigenic load is driving the inflammation, the early aging of the immune system, the senescence, and some of the metabolic derangements that we see, it just feels very similar to the HIV story. But it also says, as we're thinking about how we go about treating these things, to realize that we're not talking about one virus and one virus's replicative cycle. It won't make sense that you're going to completely control these things with a thymidine kinase inhibitor like acyclovir when you're looking at viruses that are behaving together, that there are multiple viruses, and may not even be in a replicative cycle at the time when you're treating it. And this is just a thing to make me remember to say it's more than just inflammation and immune activation. Herpes viruses directly affect mitochondria and disrupt mitochondrial function. So what are the therapeutic implications? Viral reactivation is not epiphenomenal. It's a driver. It contributes to the ongoing immune damage, and it's a logical target for intervention. But limitations. Most of our antivirals are only active when a virus is in its lytic phase of replication, and that's not what we're talking about here. These are not as susceptible as all that. In transplant populations, EBV and CMV reactivation often occurs even when you put them on decent prophylactic, even big gun, high-dose valsite prophylactic medications. So it's not easy to suppress EBV or CMV, or for that matter, HHV6. The reservoir cells, if we just talk about EBV for a moment and we think of it as a B cell virus, but it's also in the salivary glands, it's in the parotid gland. So in the B cell depletion studies that were the Norwegian colleagues did, we thought, oh, this is great because not only are they taking out B cells and dealing with autoimmunity, maybe they're going to knock down the EBV reservoir, and that could only be a good thing. But there's this reinfection coming from the parotids that can rapidly re-inoculate the system. So that's not a perfect thing. We're hoping that these newer drugs, and there are many newer drugs better than the old thymidine kinase inhibitors and zidovavir and foscavir, and not as toxic as those stronger drugs that are either already out for CMV or in early stage development. There's also 5 EBV vaccines in some stage of development and one that's already listed in clinicaltrials.gov. So that's exciting. To have an EBV vaccine is a transformative thing for human health. And I'm excited to know it's there. I'm hoping we'll be able to access it for our patients for clinical trials. But simple short courses of antivirals is not likely to be particularly helpful. So the key point here is that antiviral strategies must address the latent reservoir and the exhausted immune system, and not just acute replication, that immune system needs to be engaged if we're going to be successful. So as I said, there was the Montoya study with valganciclovir, which is a little pilot, but it looked promising for the people with high titer early antigen. The long COVID trials that they're trying to just suppress COVID, if it's replicative, and we don't know if it is. So far, the Paxlovid trial, there's been 2 of them, and they've both failed. This trial, the Maraviric trial is underway, and there's various immunomodulator trials that are getting underway. There's some pretty exciting immunomodulator trials coming along. So what is the evidence for viral persistence in long COVID? Well, it started with a series of papers. These are really important papers. This is Michael Pelosi's papers. These are both his, that are looking at plasma-based antigen persistence in COVID, in post-COVID patients, and then tissue-based T-cell activation studies. And this is an important thing to consider. This is the plasma concentration of spike protein, how much spike protein is circulating, versus severity of illness. And you can see the more spike protein, the more severely ill they are.
I'm sorry to interrupt, Nancy. You have 2 or 3 minutes to finish. We are already over time.
Oh, I'm sorry. I'm glad you told me because I'm not watching. I got chatty. I want you guys to note this paper. It's a really important paper by Rong et al. And this red stuff right here you see on that picture on the left is the cribriform plate next to the meninges. That's spike protein loaded up there. This is in an acute COVID person who died of COVID. And all these little red dots are various immune cells in the meninges responding to that spike protein. But there are other papers that have looked at long COVID in organ systems. I have that in just my next to the last slide here. And this little chart in the middle, which is finding tau and GFAP and NFL, all neurodegenerative markers in the spinal fluid of long COVID patients, which is a big concern. This is another one that's just looking at tissue. This is big numbers of people that went to surgery and they biopsied while they were in there. And this is the percent of those organ systems in people with long COVID that had measurable spike protein in skull, in liver, in GI tract, and so on. So this is my big ta-da, is our study, which is the monoclonal antibody to spike protein. The study's underway. It started 2 months ago. We're going to recruit 100 people. The person that asked about powering studies to be able to find the subgroup, this one was powered to find 25%, At the time when we designed this study, that was what we thought was the percent of people with spike protein in the plasma, but we didn't know how many had it in other tissues, so we went for everyone and not just people spike protein positive, but powered it so that if we saw a 25% response rate, we would see it. So it's 100 patients, 6 months, they get one dose, they're followed for 6 months, and then they can have a second dose, and the placebos can go open label and have a dose. So that's basically it. It covers the variants until about the middle of 2024. So we collect, that's the entry criteria, had to get 64 then. And we're measuring everything under the sun. One of the most important things with this study is that we're creating an amazing biorepository, and we're very collaborative. So keep in mind that any liquid that we could get our fingers on, plasma, you know, saliva, urine, stool, we have a biorepository that we're gathering. And so this is my conclusion slide. In conclusion, there's a lot to learn from each of these illnesses that will teach us about the other illness, particularly as it relates to the immune system, viral reactivation, viral persistence. I do think we need to think about immune recalibration and trying to find ways to shake those senescent cells back alive, if it's mTOR or if it's the LDN studies, the channelopathy interventions that Dr. Marshall Gradden is doing here and in Australia. But we have to think about these things in a more comprehensive way. I think single drug, single hits aren't going to teach us what we need to know or help our patients enough. Thank you very much.
Thank you. As we are already over time, we have time for one question, assuming that Nancy will not be here for the panel discussion.
I can come back for the panel, it's okay. If you need
We have one question there.
Thank you, Nancy. Amazing talk. It's Rowan from Precision Life. You spoke about the experience of HIV, and many of the co-infectious viruses are endemic in the population. Is there any reports in the literature that you know of whereby some individuals had a measure of resilience to that? So I'm thinking of going after some of the resilience mechanisms may find a way through this that would benefit many of the patients. I just wondered if you were aware of any clinical evidence.
The flip side of that. I do remember that in the work that was being done in HIV, if your CD4 count was toast, if you had 10 cells left, right, you should die. But many people live for years and years, despite a CD4 count of terrible. And the thing that was working in them was their innate immune system. Their NK cell function was good. So the NK cell function has a lot of psychoneuroimmunology literature because it does respond to stress in a very negative way, and it responds to stress modification to some degree. So you'll see a lot of literature there. But I think that in this instance, the NK cell has poor perforance, poor granzymes, overactivated, driven into senescence. So I think we're going to have more luck with mTOR type strategies, inhibiting the mTOR pathway, like the longevity work that people do. And then this very important work the Australians doing on the actual channelopathy. I think that if they make progress, and it looks like they're making rapid progress, that they might give us some very novel therapies.
Thank you very much. Since Nancy can be in the panel starts in about 1 hour and 15 minutes from now. I know that there are a couple of questions from online, and we will keep those for the panel. We will break for 20 minutes now, and we reconvene at 11:05 for the new session. Thank you all for this session.